Hi. Regards to my colleagues, Hartman Genrich and Bob Wirtz. They're not here, but they helped in this presentation. I'm going to be talking about the use of process discovery in healthcare process improvement. You see in this diagram here the introduction of automated process discovery in the plan phase of the Stewart-Deming Plan, Do, Check Act. And the idea here is to produce an executable bpmN model as a result of the process discovery and use that in further investigations. You see here a number of different hospital applications, electronic health records and so forth, all of them generating system logs. What we do with our system logs is we cull them and transform them into a standardized format, bpaf extended, which is what we will use to do the process discovery on. Once we have that collection of event logs, we apply artificial intelligence and data mining algorithms to create a bpmN model that has the characteristics that when you run it, it will have the same statistical behavior as the histories dictated. So we can take that and then use optimization, analytics, and simulation on that model to compare alternative proposals for process improvement. So we're going to be looking at a hospital application for dealing with supply orders. Here is one of 6 discovered processes from that problem. We're going to be focusing on stat orders. Stat orders have to be delivered as soon as possible, and we're going to see that we need to do some work. Currently, looking at the statistics in the histories, we're having an average of 20 minutes to complete stat orders. That will not do. We want it to be 10 minutes. Now, how are we going to do that? The first thing that we do is investigate our staff shortage is responsible for this. So we have a technique of using simulation to eliminate any issues in respect to staffing. And we observe that even when we do that, we're only down to 15 minutes for processing stat orders. We're still far away from what our objective is. So now we use a path pattern analyzer to look at the paths of all of the orders that were processed in the last week, 2,800 orders, and determine where the critical paths are and where the culprits are in this situation. We found a process which is on many of the critical paths. It has in it a sequence of 3 tasks. We know that those 3 tasks are part of our problem, a big part of our problem. So now we're going to go ahead and try to come up with an idea. Well, and further analysis of the task shows us that one of them, transport via cart, is the one which is introducing delays in order delivery in many, many cases. Now we have a very good idea about where to start with our improvement. Well, with the statistics, a number of proposals can be thought of. We're going to examine 2, one of which looks at, let's do training of the staff to get the staff better, and let's attack 2 of the most important tasks. The other one will only focus on technology. If we look at the comparison, this is a tool for doing cost-benefit analysis. We propose improving performance by 50%. In the second proposal, we only try to improve the technology of the tasks. It's a more expensive solution. We see in the analysis that we look at the return on investment that the first proposal, which does staff training as well, gets a return on investment within the first week of application. The second one does not. But ultimately, we'll see the second one is a better solution. So if we look at the final analysis for cost-benefit analysis, you'll see that the second one exceeds the first. Both of them meet the objective of getting the average processing time for stat orders down to 10 minutes. If we can do a little further analysis and compare the staff utilization for the 2 proposals, we see the blue, which is the second proposal, shows that solution, there's more reserve capacity in the staff for handling things. That may or may not be important. So just looking at this, we come to some conclusions about the 2 proposals. Proposal 2 has some advantages, but keep in mind, we did not quantify other possible benefits of staff training. So not everything was quantified in this. So for conclusion, we've used process discovery to reveal the actual way the work is being performed, present that knowledge in the form of an executable bpmN model that facilitates further assessment. We can systematically evaluate using simulation and so forth. the best choice. So that's a quick, use case description. And what I'm now going to focus on is details of process discovery. Okay, so I'm going to basically load an event log and transform it into a model. And you're not going to see any of this. The event log is in the format, the beat path extended format. It's an XML file. And I've generated a lot of event logs to experiment with all this technology. So I'm going to open a log. And I have many logs. Okay, there's an event log. So it starts off with the log, and I'm going to run this. Now, it built a bpmN serialization of model corresponding to what that log said it should be. And I'm going to save that. I'm going to let the algorithm finish it. It discovers other types of things as well, and I'm just going to show you some of the things that can be recorded. We were interested in the bpmN model. bpmN, there are semantic rules for all the parts of bpmN. We want that to be enforced in the model. We could have also generated a collection of simulation input information based upon the statistics. So those orders, when the orders arrived, what their characteristics were, and so forth, which is relevant to the statistics, and it's also relevant to if we want to rerun the model, corroborate it, and so forth. But I didn't do that in this case. We've exported an Optima scenario. The tool that you're looking at is called Optima, and a scenario is a model plus all of the input data associated with running that model, plus all the statistics of the results. So we've exported that because we're going to work on this in Optima. And the fourth thing is we could have exported all of this as a table that would be suitable for other products in the process mining community. They could use all this information directly. So now, I said we created a scenario. So what I'm going to do is I'm going to load that scenario. And we were looking in bpmNEXT, and we were looking in the small analysis. And the OPD folder holds discovered models. And there's our model. Okay, it's letting us rename the scenario if we want to. I don't want to do that here. So, okay, so this is a very simple top level, but it is a little interesting because there's a submodel and there's also a boundary event, and we'll just go ahead and look at the submodel. And this has got two tasks in it, one of which has interrupting and non-interrupting events. Keep in mind that a log says nothing about what are events or what are gate phase. That's not the kind of information. The logs say for events, what's the start of this? What's the end of this? Of course, in our interpretation, it corresponds to the different life cycles that are possible for activities and for processes. And those are very important in decoding the meaning of those event patterns. Okay, now I'm done with this model. We're going to go and look in more detail about discovery. Okay, so here's the same model. I have preloaded Optima with what's called a session, which consists of an arbitrary collection of scenarios, and each of the scenarios would be different stories that we tell about discovery. We've looked at this one already. I'm going to go to the next one. Now, this is a model which I used last year, a bank loan application model. And here's the whole model. There's a submodel. And we're going to talk in particular about some of the gateways that are colored, the red and the green one. And before I go into the details of what was discovered about them, you look at these structures, you see that that first gateway, one thing that can happen is the information was missing in the loan application is rejected, that's the end of it. The next thing that happens has to do with the parallel split. Now, what does this look like in the event stream? What it looks like is that check application task is followed by those other 3 tasks or an exit. And the logic has to be deduced for what that means, and it depends upon what the pattern is in respect to those other 3 tasks. Well, in every trace, you'll see either an exit from that gateway or 3 tasks that are concurrent. And that's done by analyzing the trace. So that's why it's inserted 2 gateways in there to accomplish this logic. Similar story is true about the way in which those converging parallel tasks come back together, and then another test is performed to decide whether the loan is rejected or money is dispersed. So the idea of really being able to uncover or propose a pattern of gateways that's consistent with what happened in the histories. In addition, some other things have happened. So we'll look at the red gateway, and there's an inscription below which was generated in the discovery explaining that the logic used at this gateway are probabilistic weights. And then it tells you what the weights are. That's based purely on the statistics in history. 6% of the time it went one way, 94% of the time it went the other way. And there's no other information that correlates with that. So they are properties of the loan applications, but examining those properties and doing linear regression and other data mining techniques does not discover any correlation between what happened and those values. So that's what that does. Now the green gateway, where we're making a decision about accepting the application and granting money or not, is a different story. And it says that the conclusion is that expressions can capture the logic. And what's been discovered is a property, credit record, is determining what happens. If it's greater than or equal to 550, we're granting the application and dispersing money, and otherwise we're not. So these are data mining components within this solution. I'll go on to another. This is an example which is used in BPM and method and style, Bruce's stuff. And here's the overall process. Now you notice, of course, these layouts, these are all machine-generated layouts. No one has drawn these pictures or suggested how they should look. It's not perfect, but it's pretty good. And here in this example, I want to point out a few particular items. So there's a red gateway, and it says, OK, question mark, question mark. And the idea in this gateway is that the path we take in this gateway, the yes path, should be determined by how the preceding sub-process exited. And there are several different end events in it. One of them is labeled OK. When it takes that pathway, then when we get to this gateway, we follow the yes path. Otherwise, we'll do the no. That was figured out, not that any of that structure existed in the log events themselves. Okay, the other things to point out here is you notice there's an event-based gateway in which the path is determined by what happens between when you receive a message and a 1-hour timer. And also, if you look at the C task, you'll discover there that there are both interrupting and non-interrupting boundary events on it. Just give a feeling for what's involved in figuring out from that event stream that this structure explains that pattern. Okay, so then I'll look at another example. This example is actually the whole healthcare system with 6 different sub-processes in it. I'm going to pick the process that was the culprit to show it. That's the deliver supply order. And I'm going to turn on my analytic counting. So we have control over counting all the pathways and applying any kind of filter you want to those pathways to do subselection. It's a very powerful selection apparatus for doing that. Anyway, I've selected that, and now I'm going to look at, by the way, the set of patterns on the upper right are miniature versions of all the processes. On the lower right, I have a table that correlates the discovered path patterns and their frequencies. If I go ahead and pick one of those, I'll immediately see the representation. I can't see with my glasses on here. Well, okay. So what it's doing is showing me that particular pattern, which occurred 35 times in the order history, and it's highlighting the flow nodes in that pattern. There are other apparatus in here for doing a review of each individual pattern, showing its characteristics, because the pattern not only goes through a set of flow nodes, but the delays between the different steps reflect the availability of resources and so forth. Okay, so now we're going to look at some things which in some ways simple and in other ways maybe not. So here, this is a very simple example. It's an example with a loop in it. And the green gateway is determining whether you keep going around the loop or not. And the question is, what's the logic of the green gateway? How does it determine what happens? It's also related to the fact that there are properties, and the initial values of those properties are something that was captured in the event logs. And consequently, it can make a distinction between, well, was this the initial time? Have things changed? So the green gateway, the logic for going around or not is determined by a Boolean property called latch. On the other hand, the task C actually changes the value of that property. Again, if you have event logs which do not record when property values change, you can't do this level of analysis. So one of the things that comes out of all of this work is, what is a complete story for something like BPAF, which was originally oriented around allowing you to apply analytics. If you wanted to contain more of the historical information so you can understand the gateway logic and you can understand the dependency on data. And the red inscription there shows what the criteria is, well, how it's changing the value of latch. So there are other examples like this. I won't spend as much time on them. I'm just pointing out here the gateway logic is determined on the basis of a property called loop count, and it's a numerical test. So to determine how many times you go around the loop. And on the other hand, the red inscription deals with the calculation of how the value of loop count changes. I have two more examples and then I will stop. Here's one where the example is based upon properties that are strings and expressions that are generated that are conditional expressions in Java. The last one looks like a very simple example, but the difference is there's one property called result, which is determining the branching logic, and there's another property called dur, which is determining how long a task takes. So in other words, the length of time that task executed was actually a function of the value of a property. So this is an ongoing activity building this, because as you can imagine, there can be very complicated expressions involved in determining the correlation between multiple properties and what happens at a gateway. So it's not something which says there's a close to this necessarily. The point about it is, if you look at the hospital example that I was looking at, this is much more power than that example needed. That's my story.